looking at this gas law study guide, I've simply just gone through the assignment pieces that we've done together in the course of this unit, and what I want to make sure you understand from each of them. So the gas variables POGIL, when we looked at that, we were looking at the molecular level explanations for how changing pressure and volumes occurred in response to this changing temperature or pressure. Does that make sense? And yes, error. I hate when I do that, but I didn't see it there. But typo. So in other words, why, if I heat up a gas, why does it increase the pressure if it's in a solidly sealed container?
So it excites the molecules.
Molecules get excited, so what do?
They move faster.
They move faster, so what does that do then?
More space.
They hit the side, right? If it was a flexible container, yes, it would get bigger. But if we have a solid container, they're hitting the sides, and so therefore we get more pressure. Because that's what pressure is, simply collisions with the sides. Make sense? That's what I'm meaning by that. This is straight. There are a couple of questions right in your POGIL that reflected those. Yes, ma'am?
Since the atmosphere, is it the atmosphere pushing down on the solid ground? You said that the pressure is hitting the sides.
Sure. So in this case, I'm talking about internal pressure. We had this discussion in the last class because of the same kind of issue. We're looking at both internal and external pressure. When we're talking about the gas laws, normally we're talking about the external pressure, right? If I increase the pressure on a balloon, I'm going to make the volume smaller, right? This is the relationship we talk about. For this POGO, we looked a little bit at both. Remember, it had both internal and external? So I was talking about internal pressure. As I heat the molecules, they bounce off the inside of the container's walls, and that pushes them out if it's flexible, or increases the pressure if it's not. Does that make sense? And I wish there was a different name to give it other than internal, external pressure. It just is what it is. Okay? Sir? Okay. The difference between flexible and non-flexible containers, that's what I was just talking about there. That if it is a flexible container, then the volume can change, right? It's like a balloon. It can get bigger, it can get smaller, depending on what you do to it, whether you heat it or cool it. If it's inflexible, then it's going to be one of the other pieces. Like I said, if we heat it up, the pressure is going to increase because the volume can't change. And last but not least, you learned about the direct versus inverse proportions, which goes along with those common, the gas laws, right? That Boyle's law and Charles' law and Gay-Lussac's law, the pieces that they are looking at, if one goes up, does the other go up? One goes down, the other goes down, right? Those would be direct relationships. Inverse means one goes up, the other goes down. One goes up, the other goes down. One goes down, the other goes up. We cool? Together. Inverse is opposite. Yep. Absolutely. Yes, please. Exactly. The pressure would stay the same because the volume changes. The shape of the container changes to expand or contract. Exactly. Yep. And again, please understand, nothing here was not covered in the lab that we did. Nothing was not, and even the questions we answered together. We went through all those pieces. The ideal gas law, you should be comfortable if I give you P, V, and N, you should be able to find T. Right? If I give you T and N and V, you should find P, whatever combination of those four pieces. You should be comfortable knowing which R to use. You don't have to memorize them. I'll give them to you. I'm going to give you the same chart that's in your textbook, but you have to know which R to pick. How do you know? One word. The name, they're all named R. The units. It's all about the units, right? And even, I would even say it's all about the pressure units. Because for temperature, we're always using Kelvin. For volume, we're always using liters. And if they're not at those, you have to change them. So otherwise, it's simply about the pressure. That's the only thing different in the R's you were given. It's just the pressure units. Mm-hmm.
change temperature in Celsius,
Mm-hmm.
do you like change the temperature in Kelvin and then switch it back to Kelvin?
Sure. Right. So they give it to you in Celsius and they want it in Celsius. You'd have to first switch it to Kelvin, do the math, and then switch it back. It would. So if you have two positive Celsius numbers, it won't matter. You with me? Because the proportion's the same. But if you have a positive and a negative, or you have a positive and a 0, it definitely does. So that's why it's better just go ahead and change them. It's 273. Add or subtract.
Switch from Celsius back to Kelvin.
Yep.
I mean, to switch from Kelvin to Celsius.
Yes.
You have to subtract the number by 273.
Yes. Mhm. Yes. Yep. Kelvin is Celsius plus 273. I'll put it up here. That way you can see it. Kelvin is Celsius plus 273. Right? Ta-da! But if I want Celsius, what would I do? There you go. Does that make sense? Of course, you know, how do I change from milliliters to liters? If you don't know this by now, I'm a little nervous. It's 1,000, right? 1,000 milliliters in 1 liter. Our common gases lab, these are just some of the questions that we learned about these gases. Why the litmus paper turned blue when we exposed it to ammonia? Because ammonia is a base, right? It has a pH that's very high. And litmus paper, when you expose it to a base, it turns blue. Blue base, red for acid. Why the match glow brighter? This class, I don't think we had anybody who got that piece. Or nearly burst back into flames when we held it in the oxygen. Because oxygen supports burning, right? It makes it want to burn more. So yet that freshly blown out match, when you put it in oxygen, it wants to catch fire again. Does that make sense? Why did the experiment with nitrogen dioxide, why did we perform that in the fume hood? It's a poisonous gas, right? It is a very dangerous gas. And we don't want that spread around the room here, right? So that quickly evaporates, or not evaporates, but evacuates it outside. And last but not least, why did the hydrogen pop when we flame tested it, but the oxygen didn't? Hydrogen is combustible. It will burn. Will oxygen burn? No. Everyone thinks it does, but it doesn't. Otherwise, every time we lit a match, the whole world would blow up. This would be a slight issue. Are we cool? Deflategate, we spent some good time talking about that. All I really want you to be able to do, you don't have to give me super tons of details, but all I want you to be able to tell me as far as Deflategate goes is, can you use the gas laws? Can you talk about how pressure and temperature affect the volume? I hope you can, right? As temperature goes down, pressure goes down, right? Volume goes down. As pressure goes down, volume goes down as well, right? So if I take something from a hot, pressurized locker room, right, into a cold, less pressurized field, what should happen to the volume? It should go down, right? Was it enough to deal with the errors they found? There again, that's up for interpretation, but the science certainly made sense that, hey, we could certainly see a drop in pressure. Does that make sense? I'm not looking for you to give me the whole, oh, here are the numbers and it was this temperature. And no, you don't have to give me all that. No. I'll be impressed, but no. And last but not least, using those gas laws. Boyle's law, Charles' law, Gay-Lussac's law, combined gas law. This is numbers 1 to 13. You did yesterday, well, 2 days ago, and then the problems that we did yesterday, which we'll talk about in a moment. Boyle's law deals with what? Can you remind me? Pressure and volume. Yep. Charles' law deals with volume and temperature. Gay-Lussac's is pressure and temperature, and then combined is all of them, right? Does that make sense? So I'm not going to ask you to spit out the equations for them all. I mean, you have to use combined gas law. That's the one I recommended you be comfortable with because you can use it for everything. But I will ask you, which law shows a inverse relationship between pressure and temperature? And does that make sense? Or which one shows a direct relationship between volume and pressure? And you answer. Okay. Any questions there? I think this is pretty straightforward. As I increase pressure, I decrease volume. So that would be inverse.
Okay, so not pressure and temperature happen,
Right. As I increase temperature, I increase pressure. Yep. Again, think about you're heating that balloon. It's going to get bigger and bigger and bigger, like a hot air balloon, right? Are you with me, my friends? Any other questions there? Yes? No, I will give you the R's. I don't want you to spend oodles and oodles of time trying to memorize equations. Ideal gas law, combined gas law. If you know those two, you're fine. Right? Don't waste oodles of brain power on all the different other pieces. But again, I do want you to know what concepts they deal with. Yes, ma'am.
I get confused sometimes as to when we're supposed to use the R value.
R is only for ideal gas law. An ideal gas law is when, if I got pressure, volume, temperature, and the amount of gas, right? Those are my 4 variables. You'll know 3 of them, and you've got to find the 4th one.
So like if you're using the pressure, volume,
Mm-hmm.
equals pressure times volume. So if like they said it was 0.533 atmosphere pressure,
Mm-hmm.
you wouldn't multiply that by the R value, you just leave it and like that.
If you're dealing with, so ideal gas law is I've got one of these 4 guys, and I'm missing one of those 4, and I have to find it. The other gas laws are I've got some temperature and pressure initially, and I want to change the temperature and know what the new pressure is. Those guys you don't use R.
Okay.
They don't need it. We don't need them.
Okay.
Right? It's only for the ideal gas law. That's when you would use R.
You won't need to convert between R values.
No, excuse me. I'm literally going to photocopy the R chart from your textbook and give it to you. Yeah, because you just have to know which one. And again, how do you know? It's about the units. The units of pressure determine that. Sir? Inverse means if I increase this, then the other one goes down. So what 2 pieces, if I increase one, it causes the other to decrease? If I increase the pressure, what happens to the volume? It goes down. Again, think about I'm squeezing, right? And then we're talking about external pressure to go back to that, Rachel. If I external pressure, I'm squeezing it, it's going to go down in volume. So that's our inverse relationship.
Wait, so English accent, the only one that's inverse, right?
Charles is 2. Sorry, these 2. Boyle's law is the only inverse. And Gay-Lussac's and Charles are both direct. Because if I increase temperature, I increase volume. If I increase temperature, I increase pressure.
So just to make sure, the gas laws, that's
Excuse me.
external pressure.
Yes.
The ideal gas law is or is that still external?
This is a good question. The ideal gas law is pressure. It is internal.
Is it internal?
Yeah. Again, I'm not going to ask you to get too technical as far as that goes. The combined gas law is combining all the 3 pieces together, so it's both. Again, that's why you have P1, V1 over T1, right? These 2 are inverse, but these are direct. So, yeah, it's both.
So you said that Charles and
Right, because if I increase the pressure, I'm going to increase temperature. If I increase the temperature, I'm going to increase the volume. Yep. Again, just to make the equation work, you have to do it that way. Yes, ma'am? Right, now they put it over here, P2, V2 over T2. Yeah, that's our combined gas law. Yep. And of course, ideal is PV equals nRT. Pivnert. That's what it always looks like whenever I see it. I don't say it, but that's what it looks like in my mind. Any questions there? It's good. I appreciate the questions.
With gas variables,
Mm-hmm.
gas variables, how long that we were dealing with external.
So it dealt with both. Remember, it had both that were in there. Yeah. So, when we're talking about the flexible versus non-flexible piece, it was dealing with both. We were dealing mostly with that internal pressure there. We cool here? Again, I'm not trying to rush you. These are good questions because I'm not here tomorrow. So today's the day to ask. I'm not going to be here. We have one personal day that we can take like the entire year, and tomorrow is my day. And it's going to be raining the whole stupid day. Anyway, sorry. It's life. One, that's it. Yeah. Well, okay, one first semester, one second semester. You're right. You're right. But we rarely. Again, I worked for 10 plus years and hardly ever took it. Because again, it's more of a pain to be gone than it is to stay, truthfully. I kid you not. But I'm not trying to record all of that. Any other questions? I'm going to stop this recording. We're good? All right.